Hi everyone, my name is Alexander Demidovsky and I am a PhD student in the High School of Economics in Russia. My talk today is about exploring neural Turing machines applicability in neural-symbolic decision support systems. So, what is decision support system and what is a neural-symbolic decision support system? So first of all, let's understand that decision support systems are the systems that actually are designed to help the decision maker to make the final choice. So say we have several alternatives, we have several criteria, and we ask several experts to assess the alternatives for the given criteria, and then we give all those assessments to some black box system that makes a recommendation for us as a decision maker what is an alternative to choose. So in general, this is what decision support system can look like. And as it is a quite demanded thing, there are several requirements from the business side that should be satisfied in every decision support system, or DSS for short. So first of all, those systems should be explainable. So a decision maker should understand how the decision was made, how the recommendation was made, instead of just getting the number or a vector of numbers from the black box. They need to understand why the decision support system decided that this alternative is better than other, and so on. Another thing is that the decision support systems should be scalable and qualitative at the same time. Scalability through the use cases is what I'm talking about. So there is no reason to create decision support system for one particular use case, while the ideal decision support system should adopt just not only to the new use case, but even within single use case, there should be an opportunity for the decision support system to once getting the new data, get better results, producing better suggestions. And also the decision support system should be autonomous. At the same time, there are two paradigms that we need to consider. One of them is a symbolic paradigm, which considers every computation as a symbols manipulation. So symbolic paradigm and decision support systems, conventional support systems, are made symbolic, so they are highly interpretable by design, they're easy to control, and they allow to create a predefined set of rules. At the same time, this is a disadvantage of symbolic computations and symbolic systems, and it is known as a grounding problem. So let's say a programmer who designed a system, they included rules to that system that are defined by their own picture of the world. So, and this makes the system biased. And of course, we do not want to make a system biased. At the same time, the sub-symbolic paradigm is provides us with a scalable and distributed computations. Of course, we have learnable systems, and they are quite quick. Once they're trained, the inference of neural networks is quite quick as far as we know. So making a decision support system a neural symbolic one can be quite promising. And the question, and this only brings us to new questions of how to make that, when. And important note here is that a decision support system still should be hybrid, so they cannot just become sub-symbolic. And that's because of the interpretability. So we all know that neural networks are quite hard to interpret, and there is even the scientific field, which is called explainable AI, that tries to make some insights how the network made their decision. So for decision support systems, the whole system should be transparent and explainable. In our case, we consider the linguistic decision making field, where the criteria are not only qualitative but also quantitative. So when we have quantitative assessments, we have numbers as the assessments. When we have qualitative assessments, we have some linguistic form, for example, poor badge or good badge, and so on. And the fuzzy assessments that are provided by the expert, they are in the linguistic form. They can be comparative, they can be not sure. So the assessments are very fuzzy, and the two-tuple model and its derivatives allows us to express the linguistic decision making when we have such assessments in their mathematical forms. So when we have a set of two-tuple assessments, we need to translate them to numbers by using a special translation rule that allows us not to lose the information. And then by using the special algorithms, or as they call in the field, operators, we make the aggregation process. Finally, we get the number, and then we can translate that number back to the linguistic scale, thus making the decision-making process transparent for the decision maker. So they have assessments expressed in the natural language form, and they have the final decision made in the in the natural language form. So it is quite convenient. However, the question is whether the assessment aggregation can be subsymbolic. So we do not need the interpretability in the phase of aggregation. We need interpretability at the beginning of the aggregation and at the end. And to answer that question, we propose to use the neural Turing machines. So in general, neural Turing machine are example of a memory-augmented neural networks that have the core idea that the computation and the memory should be different. So they should be separated. And here on the slides, we can see that there is a controller network that receives the input and then manipulates the external memory with the use of so-called read and write heads that make the change to the external memory. So write head changes the memory, and read so in turn allows us to get some values from the external memory. And as the system is fully differentiable, we can get this whole system trained. And it was demonstrated that NTMs can learn faster and generalize better than LSTMs for a bunch of tasks. So I recommend you to watch this video to get more insights. This is a video of the author of the recent Nature Communications article. So I really recommend to watch that. So what's next? The next thing is about the details how the neural Turing machine work. So neural Turing machines accept a sequence of vectors as an input and returns a sequence of vectors as an output. And as it is a fully dynamic recurrent neural network, the length of input sequence and the length of output sequence can be different. So each time, at each period of time, we feed a single vector to the NTM, and when the sequence finishes, we can get the output result and estimate it how well the neural network solves a particular use case. So, and solving any use case with the NTM requires translating input data in the corresponding sequential format. So NTM as an architecture can solve multiple tasks. The only thing is how to interpret and how to translate the input data, the raw data, in the required format. So in our case, as we are going to solve the arithmetical task, and the idea is that while the MTA operator requires arithmetical operations, then if we express several arithmetic operations in form of neural Turing machines, we can make the whole aggregation in a neural form or make it subsymbolic. So training NTM to solve arithmetical tasks requires encoding arithmetical expressions in sequential format. So, and we have used the known format for expressing arithmetical operations that were proposed by Castellini in 2019, which assumes that we translate whole numbers as binary strings of the given length in a little endian format. So for example, this is the input to the NTM. So we have a 14 in a little endian binary form. Then we have a marker which separates first number and second number. And then there is a marker of the end of the expression and the answer that the network should learn to predict. So in general, we try to train the NTM to make this simple sum. So as a result, we can see that even for 10-bit numbers, we have Betty convergence. So the network converges and solves the arithmetic sum tasks for two 10-bit numbers. So as regarding the software solution, we are basing our implementation on the existing implementation of neural Turing machines. However, we have made a considerable improvement of translated it to the TensorFlow 2.3, as the previous version that the original implementation was based on is deprecated by the maintainers. And also we added the supported task, which is the sum. So to make the conclusion, we can say that elaborating hybrid decision support systems is an actual task. Decision support systems cannot be fully sub-symbolic. Certain parts should be symbolic due to interpretability requirements. We know that NTM can perform basic arithmetic operations, so we can use it for expressing certain parts of the decision support systems. And our next steps would be to try to educate, to train NTM to perform an averaging operator, and finally to get the whole linguistic operator expressed as a trained NTM. So that's practically it. Thank you very much for attention, and I would be glad to get your feedback. Please write to me by using one of these emails. Thank you again.